In this series of videos I'm attempting to repair and restore this HP9845B vintage computer. So far in this series I've stripped this unit down into its major sub-assemblies, gone through the power supply, corrected a few issues with that, cleaned up the various parts, the backplane, and it's in fundamentally good condition, but it just does not run at all. It doesn't get very far into the startup, doesn't even beep. I don't know if it's a faulty speaker, but it's just not starting up and getting past the initial startup phase, and the startup for this is fairly unusual. And I've explained it in a previous video, but just to recap, there are two processors. There's the LPU on the right, and there's the PPU on the left. That's a language processor and the peripheral processor, and they're two effectively independent computers, but they do interact and they perform specific tasks within the overall operation of the system. So each one is kind of self-contained. It's got the processor board, a ROM and RAM card, and it's fairly basic in the general way it works, but in the actual way the system operates, it's very complex. And if you've seen other repair videos on various HP machines of this era that use this type of processor, this one has, of course, two. And not only that, but it also has two 16-bit buses. It's got the X and the Y bus, not just one bus, each of which is bidirectional, and each of which is multiplexed between address and data. So it's a very complex system, much more so than the smaller brothers in this range. And it makes it quite a challenge to work on, but if you kind of follow it through in a logical way, it's not difficult, and it is quite a lot of fun to work on something this complex. Now, unfortunately, the schematics I have are not particularly clear, so I can't really blow them up to any large extent. But if we have a quick look, I don't know how much of this you'll be able to see. The two processor cards are very similar. There's some slight variations, and the two ROM and RAM cards are identical. The only difference between them is the contents of the ROMs and one jumper. There's a jumper in the bottom left hand corner that selects either LPU or PPU. But on the schematic, what we have is the hybrid module. That's this thing at the top. This is the actual processor. That's the thing underneath the big heatsink. And then all this down here is the buffering and multiplexing for the two buses, and also the block selection. So the memory in this machine is divided into blocks, and each of those blocks can be selected, and then of course the machine can select the particular byte within the block. So what we have for each of the two buses are two sets of buffers. There's a couple of latches, they're 8 bits each, and it's 16-bit wide bus, so there's two. So there are two latches that latch the address, and then there are two bidirectional buffers that allow data to be put out onto the bus and read back from the bus, and then you've got the identical arrangement on the second bus. And the two processors are identical. The other one's very similar to this. The only real difference is in the way the clock circuit's arranged. The clock's fairly complicated because it has to synchronize the operation of the two processors. But again, it's not complicated. You can just check the clocks on the actual processor itself and see if they're present. I've done that, and they are. I've probed around with the scope since the last video and found various signals that just do not look right, and I think we've got some failing buffers and latches on this. But the way that the system accesses ROM or RAM, it puts out the address bus. There are incidentally timing diagrams for this in the original HP documentation, and in some ways they look wrong, but they're not. This is actually the way the system works. And when I say they look wrong, as I go through this brief explanation, I'll point out where it looks wrong, but why it's the way the system works. So to access RAM or ROM, the CPU will put out the address bus. That will go into the latches that latch the data out onto the address. That then goes through to the memory card, and there are lots of different types of memory cards for this, so I'm just giving you an example here. This is the basic CPU ROM and RAM card. So what we have is the ROMs at the top, and they're in pairs. So this ROM and this ROM are one 16-bit ROM in effect, and they're both selected together. But the data and the addresses come in through these lines, and so there's no latch on this board. You'd expect there to be a latch on here, but there isn't. The data is latched at the CPU end, so it's actually latched at this end in these latches, and that latches the address. That then selects the appropriate address in the ROM, and then it switches partway through the cycle to reading the data back in. So the address is put on to the address bus, makes its way through the buffer, and then it selects the appropriate address in the ROM. The chip is selected, the data is put out onto the bus, the output is enabled, and at the same time the CPU reads the data. And if you look at the timing diagram, it seems to do that at the same time as it terminates the cycle, but that's the way it actually does it. It's kind of relying on the propagation delays within the system to make sure the data is still stable at the point where it reads it, and it works very well. There's plenty of time for it to do that. It only takes a few nanoseconds for the processor to read the data, but the timing diagrams kind of look wrong, but they are right, and if you put a scope on them, that's exactly how the system operates. But it means it's quite a complex series of events to either write data to the RAM or to read data from the ROM, and that's what I want to check in this video, to see if we can actually get the data out of the ROM. As you can see, I've got the logic analyzer attached, and we'll look at that in a minute. But when I first started doing this, I've been working on this for a few hours. When I first started probing around and attaching the logic analyzer, I was basically getting garbage out of the ROM. So when I was looking at the data on the logic analyzer, which is attached here, this is attached on the inside of these buffers, so it's attached directly to the output of the CPU, not the output of these. So I started scoping on the output of these, and I was getting nonsense on them, and the startup sequence is fairly well documented, so I knew what I was looking for. That's not what I was getting. I haven't changed any parts, but it does now seem to be behaving itself a lot better. What I found was one of the little tabs on the edge connector on the motherboard that this plugs into, it had a very hard build-up of something. It looks like some liquid had been spilt down into the machine at some point, and it had kind of congealed on the surface of one of those connections. Now, I have cleaned this when I cleaned the motherboard, but it was fairly hard to spot, and it was pushing the little tab back out of the way. It wasn't making good contact, and that was on one of the bank select, or the group select lines. And I cleaned that, and then I started getting something on the scope that looked a lot more reasonable. A lot of the signals still look very poor, so I still think we've got other issues here. I still don't think it's working. In fact, I know it's not working because it doesn't get through the startup. But what we now have is the system attempting to start up. We've got the two ROM boards, so these are the basic ROM-RAM boards. That's the one that is associated with each of the two processors. So we've got the one on the left, which has 32K of RAM, 64K of ROM. That's the one over there on the left. And then we have the one on the right here. This is the one we're looking at now, which has 64K of RAM and 64K of ROM. And in particular, we're interested in the first pairs of ROMs. So that's this ROM and this ROM that act as a pair, and these two that act as a pair. So this is block 5. That's the base ROM block, for the PPU, and this is block 3, which is the base ROM for the LPU. When we boot this machine up, both processors initially start looking at this ROM in block 5. In fact, they try to read the ROM in block 25, which is the test ROM, but I don't have it fitted. And if you don't have it fitted, it will then jump through to, both processors will then jump through to block 5. They will then start trying to determine which processor they are. I explained this in the previous video. So in the LPU, the halt input to the processor, so that's this line up here, the halt line to the processor is grounded. It's connected direct to ground. You probably can't see it, but it's connected direct to ground. So it will always return a low value when the processor reads it. But the same line on the PPU is connected to the vertical drive signal from the monitor, which is, as you can see, not plugged in. The reason it does that is, as far as I can determine, is because that line, the signal coming from the CRT, is used to synchronize the writing of data to the monitor with the cycles of the processor. So if you've watched my series on the Z80 design that I'm doing, then you'll know why that's important. But it's using this halt line not really as a halt line, it's using it as a line to synchronize the data output to the monitor, and it only needs to do that for the PPU because the PPU is responsible for sending data to the monitor. The LPU doesn't send data to the monitor, so it doesn't need to do that. But either way, when the system boots up, it needs to determine which of the two processors they are, because they're otherwise identical. So they start off by examining the state of the halt line, and they should then jump through to their own block of code. So the PPU should jump through to the initialization code in block 5, and the LPU should jump through to the initialization block in block 3, or initialization code in block 3. And we should see that on the logic analyzer. It will start off both in block 5, but then after a few milliseconds we should see the LPU branch to block 3. So the reason it might take a few milliseconds, in fact the reason it will take a few milliseconds, is because both processors are actually executing the same code. And what they do is they look at the state of the halt line, and on the PPU the halt line will look like this. On the LPU it's of course continuously low, but they don't know which is which to start with. But when the PPU samples the line, it might sample it at this point where it will be low, and rather than just making the assumption that it's the LPU, which would be wrong, it samples it, and if it's high it knows it's the PPU, so it moves on. But if it happens to be low, because it samples at this point, it waits for about 4 milliseconds, samples again. If it's still low, it knows it's the LPU, but if it's now high, it knows it's the PPU, and that's how it determines which is which. So what we expect to see on the logic analyzer is initially the LPU, after a reset, should try to jump to the ROM in block 25. That's not here, so it should fairly quickly branch and jump to the ROM in block 5. It should then figure out after a short delay, about 4 milliseconds, that it's the LPU, and it should then branch to block 3. And as I said, we should see that on the logic analyzer. So I'm going to move the camera so you can see the logic analyzer screen, and then we'll boot this up and see what happens. So looking at the logic analyzer screen, what I'll do now is start up the HP9845. So it's not running, of course, but if I press the stop button on the keyboard, then it halts the machine. So what I'm going to do you can see on the logic analyzer I've got it to trigger when the init line goes high. So this is especially the reset line. So if I press and hold the stop key on the machine, that will force this line low, will arm the analyzer, and then I'll release the key and it should start capturing data as soon as the reset line goes high. So I'll do that now, press the key, we'll arm the analyzer, I'll release the key, and it's now captured some data. So if we start looking through the data, we should see that it starts off in block 25. So what we've got on the analyzer here is the top red trace is the multiplexed data and address bus, and the blue trace is the bank select bus. What we're looking at down here, and the two lines we're most interested in, are the memory select line, the SMC line, and the STM line. In these analyzers you can actually demultiplex the multiplex data and address bus. All you do is you select an appropriate clock source for the sample point. In this case you can use SMC and STM to qualify the clock source as to when you want to capture data, and then you'd have two bus displays, one for data, one for address. I tend not to do that. You can just as easily look at the STM line and see what the actual data is or the address is at the time and determine whether it's address or data. Okay, so I'll start scrolling through this. You can see we've started at bank 25, which is what it should do, but you can see it's also now showing a value there of 0, which is because we don't have the ROM fitted. We'll keep scrolling across, and what we can see here is the SMC line has dropped. So it's really at this point when it reads the data. So it's the rising edge here, it's reading the data, it's 0 because the ROM isn't there, and so it should then branch to bank 5, which, as you can see, that's exactly what it's doing. You can kind of ignore some of these transient values. That's just because of the way that the system makes use of the multiplexed bus. It's only the edges that we're interested in for the SMC and STM signals. Okay, it then branches to address 21, and 21 is effectively the reset vector. In fact, it's 20 is a reset vector, but it ends up at 21, and that's where both processors will start executing code from. But even though we are looking at the LPU, which has its ROM code in bank 3, as I said, it starts off in bank 5, so they can both use the same code. What it then does is it starts checking the values it finds for the halt line, and it's looking to see if the halt line is active, and you can see here it's jumped to address 200, and again both processors will do that. That address 200 is the start of the initialization code for both of them, and in this case they will both use the initialization code in bank 5, and so you can see so far it's doing the right thing. The data values look correct. Also, the important thing here is you can see the address is incrementing. We're now at 201, and it should get up to about 209 and just start looping. If you look at the source code, 209 is especially a wait loop. This is where the 4 millisecond wait is. So if we keep going, we should see that incrementing at 204, 205, 207, 208, 209. So you can see it's continually jumping around 209. We're still in bank 5. And we'll keep seeing 209. It's just going round and round in circles in a very tight delay loop. It's just basically waiting now for 4 milliseconds or thereabouts. So what we can do is, rather than scrolling through this for the next hour, I'll jump us forward and we'll go through to 1 millisecond. It should still be in bank 5 if this is working. So it's still in the same part of code. You can still You can see it's still jumping to address 209 and just going round in circles. So we'll go up to 2 milliseconds and it should still be in the same bit of code, which it is. We'll go to 3 milliseconds. See, we're still in the same block of code. So it's looking good so far. We've got 4 milliseconds. So it is successfully reading the correct information from the PPU bank 5 ROM, and that's what we want to see. So still in the same part. Now it's actually about 4.3 milliseconds I think it is, and it takes quite a long time to scroll through, so we'll go up to 4.3, scroll through, and we're still at 209. I'll keep scrolling through, and now it's changed. You can see it's gone to 20A, so it has now got to the end of the delay loop. It's going to sample the halt line again, and if it is now high, which in this case it shouldn't be, we'll have an error. If it's low, which it should be because we're in the LPU, it should now branch to bank 3. So we should see it at some point fairly soon. If it's working, jump to a different bank. And it has done. So you can see now it's jumped to bank 3, which is the that's the base ROM pair for the LPU. So it's done exactly what it should do. Not only that, but it's gone to the correct address, 200. So this is the initialization code for the LPU. I've printed off the block of code at that point. I don't know how well you can see this, I'm going to light across. So if we look at the code, then the first value we should see at that address is 0021. So that's what the LPU should now read from that address. So we should see a value of 21. And as you can see here, and like I said, what we're interested in here is the rising edge of the SMC line. This is the point at which the processor reads in the data from the multiplex bus. So if we follow this up, you can see the value it would have read is 21, which is exactly the value it should. The next value we're looking for at address 201 is 301E. So if we keep scrolling across, we should see that address if the processor is working, and indeed we're getting 201 in the correct bank, and the value we're seeing when the rising edge of SMC occurs is 301E, which is correct. If you look at the next value down for 202, it's 006C. So we'll go across and see if that appears. We've got address 203 in the correct bank. So on the rising edge, we're getting 33FF, and as you can see, that's the correct value, 33FF. Next value should be 03FF. So 204, the same bank. We are getting 03FF. We'll do a couple more. So the next one should be 106C. So 205, and we are indeed on the rising edge of SMC. We're getting 106C. So we'll do one last one, and the next one should be 6C02. And it is indeed 6C02. So this processor appears to be working correctly, at least in the very early part of the cycle. So what we'll do in the next video is this exact same process, but for the PPU, and see if that is also correctly getting past this initial phase of the startup. But hopefully you can see how this works, and how it's relatively simple to do this basic testing. Now if we were getting the wrong values, then we'd have to start looking into the multiplexers, the ROMs, bidirectional buffers, latches, all sorts of things that are involved in this. So it's quite good news that we're seeing it get this far, and also that it seems to be reliably reading the data, especially considering looking at the state of some of the signals that are on the bus. So as I said, next video we'll do this same exercise for the PPU and see how far that one gets.